Hello everyone, welcome. This is Steve Cefaletto, a professor at Erie Community College near Buffalo, New York, and I teach a lithographic printing press lecture and lab class. This video is going to discuss atmospheric conditions in my printing lab back in 2013. The purpose is so that we understand what temperature and relative humidity are and what their relationship is to each other. I want to make sure that we can define and convert between the Fahrenheit and the Celsius scale. And again, talk about the negative effects that relative humidity, either too high or too low, will have on paper. So in one of my earlier lectures, we talked about the international standards units. And for temperature, it's the Celsius scale, abbreviated degrees C. This is formally called centigrade. Centigrade, centa meaning 100, grade meaning a scale. So if you go from 0 to 100, that's the centigrade or the Celsius scale. There's the Fahrenheit scale, and it used two benchmark states of matter where water freezes is a solid and where water boils becomes a vapor gas. That's 32 degrees Fahrenheit and 212 degrees Fahrenheit. And then the third temperature scale we have is Kelvin, and Kelvin is typically used for measuring color temperature of light sources. For example, when we talk about D50, D means daylight, 50 means 5,000 Kelvin or 5K. So again, temperature is you're cold, you're warm, you're hot, and we have three different scales, and we have definitions of the three states of matter here. Now, if you convert Fahrenheit to Celsius or Celsius into Fahrenheit, here's the equation or the formula for doing that. And the result is a straight line. So it's a linear relationship. It's not a curve. And if you want to define a straight line, the equation is y equals mx plus b, where m is the slope. And of course, in Excel, we can calculate the slope. And this r squared is a correlation coefficient telling you how strong that relationship is. When it's 1, it's perfect. So we had a correlation coefficient of 1, which means we have a perfect correlation here. So when you're 32 degrees Fahrenheit, you're 0 degrees Celsius. And when you're 212 degrees Fahrenheit, you're 100 degrees Celsius. Now, the sensor, or the probe that I used, was made from a company called Omega. This is a battery-operated portable sensor that stores the data, and then you can download it later via a USB. This cost about $135, and it records temperature, relative humidity, and the dew point. So when we take this data and download it into Excel, we were collecting the data every 30 minutes, so twice an hour, which is 48 times a day. I have over 18,000 data points collected. It measured the temperature, the humidity, and the dew point. We calculated the maximum high, the minimum low, compared those two, subtracted them, and got the range. Calculated the average or the mean, and calculated the standard deviation. Now, standard deviation, as you recall from an earlier lecture, is the amount of variation. The lower the number, the better. The higher the number, the more variation there is, so that's typically a bad situation. Standard deviations, if you have just one of them, that's 68% or 2/3 of a population. If you have the two standard deviations, that's 95% of the population, which means 5% or 1/20th is outside of that. And if you have plus or minus 3 standard deviations, you have nearly all, most of it, 99.7%. So the standard deviation on temperature was very low, but the standard deviation on humidity was very high. And the question you might want to ask is, why is this low and why is that high? That's because during the cold winter months, I could turn the heater on and bring the cold temperatures up. But during the humid winter months without any air conditioning, there's no way for me to bring the relative humidity down, because air conditioning automatically also dehumidifies the air. So from this data, we can plot it. And here's my plot of temperature. So here on the x-axis on the horizontal bottom is the month of the year for 2013. The vertical column to the left, the y-axis here, is temperature in Fahrenheit. And you can see the data fluctuates. We can find a trend line here, which is a slight curve, not perfectly linear or straight line, but a curve. And if the temperature is cold, if I turn the heater on, I can bring the temperatures up. If the temperatures are hot without any air conditioning, there's no way for me to bring these temperatures down. So that's why you see more of the spikes and peaks on the high temperatures than you do on the low temperatures. Now let's take a look at the relative humidity. Again, time, month of the year, and the relative humidity. So during the cold winter months of January and February and March, we have low relative humidities, 15, 20, 25%. During the spring, April and March, the relative humidity increases. During the summer months of June, July, and August, we have very high relative humidities, could be as much as 80, 85%. Then in the fall, September and October, the relative humidities drop. And then back into the winter months again, November, December, and January, the relative humidities are low. So at first look, this looks like a normal bell-shaped curve. However, because it repeats, it's a cyclical pattern, and that cyclical pattern is called a sine wave or sinusoidal. Again, we have a lot of variation in the standard deviation, and that's because during the hot, humid summer months, I don't have any air conditioning to bring the temperature down, which would automatically also dehumidify the air. Now, during the dry winter months, what we would also like to have is have humidification, where we can add water to the air, and that would be with spray misters that spray water vapor into the air. Now, historically, if we went to the National Weather Service and looked up Buffalo, New York, this is the historical data from 1938 to 2020. The dark blue data is actual daily temperatures. The red are the maximum highs for that range of time, and the cyans are the lows, the minimums for that range of time. In this center lane here is this mustard yellow brown. Gold color is the averages that we want to be within. So hopefully the data plots within the brown range here and not on the high side or the low side. But again, historically, over this very long time frame, we can see that we have the sine wave. During the winter months, we're low in temperature, and during the summer months, we're high in temperature. Okay. And by the way, this is the website that you can go to find the data for your city across the country. All right, so getting back to the purpose of this experiment or this project, we want to make sure we understand what the temperature options are for Fahrenheit, Celsius, centigrade, or Kelvin. We want to know how to convert between any of those scales using the conversion formulas or equations. And we want to know that that relationship is linear. And then we also want to talk about the effects it has on paper. So let me just have a few highlights here. This was the actual data recorder. It cost me $135. One of the reasons why the temperature may be fluctuating is because we had 3 different instructors that may have a personal preference or bias for how they want the temperature set. Interestingly, air conditioning, modern electric air conditioning, was invented in 1902 in Buffalo, New York, by a gentleman named Carrier, who later made a company called Carrier Air Conditioning that moved to Syracuse, New York. But the reason why air conditioning was invented in the first place was for a printer in New York City that was having register problems with the paper. Very interesting fact about printing. My press lab did not get air conditioning until 2015, and one of the problems we were having prior to that was that we were getting a lot of condensation and sweat on the metal parts. So my 6 metal printing presses and my paper cutter and my folder were all rusting severely because of the dew point and the condensation. Again, here's the equations and the formulas for converting Celsius into Fahrenheit and Fahrenheit into Celsius. A reminder about the equation for a straight line, y equals mx plus b, where m is the slope. Yes, 2 points to find a straight line, but if you have a third point, you can confirm and verify that it is a straight line and not a curve. Just before Easter of 2020, the novel coronavirus COVID-19 hit. So we're all in isolation and quarantine here, basically, social distancing. So the specification for the human body's normal body temperature is 98.6. But it fluctuates. It fluctuates depending on your sex, on your age, and the time of the day. So there's got to be a tolerance limit here, and the tolerance limit is plus or minus 2.3 degrees, and that's based on 3 times the standard deviation, where the single standard deviation is 0.72. So technically, you can't really say you have a fever until you have a temperature over 100 degrees based on the standard deviation. Let's make sure we understand some basic terms and definitions. Condensation is a phase change when you go from a liquid you go from a vapor gas into a liquid. That's condensation. Dew is the result of condensation. That's the water droplets that form on a surface. If that surface is cold, then it'll be frost. Dew point is the temperature where the dew will form. And humidity, or relative humidity, is the amount of water vapor in the air. Hotter temperatures can hold more. Lower temperatures, colder temperatures can hold less. So when it's raining or when there's fog, you're at very high relative humidities. Now let's talk about the effect it has on paper. Paper is made out of cellulose fiber, which is hygroscopic, which means it's going to exchange moisture with its surrounding environment, the air. So that exchange can absorb or gain, or it can release and lose, and it does that until it reaches a balance or an equilibrium. Hopefully, the paper is at 45% relative humidity, and that's the environment we want to be in. Now, when you buy digital papers, or you buy paper for a heat set web press, or you buy paper for a sheet fed press, you buy them at different moisture contents or relative humidities. That's because in lithography, we add emulsified water or fountain solution into the ink. That water gets transferred from the ink rollers to the plate, from the plate to the rubber offset blanket, and from the blanket to the paper. If the paper is too dry and we expose it to moisture, it will curl. That's why we buy the paper slightly on the wet side, so it doesn't curl as much. Digital papers, the papers are going to be fused. The toner is going to be fused or melted onto the paper. So it's going to go through a heater or a dryer or an oven. So if the paper is too wet and we dry the moisture out, it's going to curl quite a bit. So we want the paper to be on the dry side for digital. We should know that the cellulose fibers grow 5 times more across their width, across their diameter, than they do along their length. That means that paper is not dimensionally stable. It will change its size, its dimension, as you change the relative humidity. Grain direction is very important for printing on the press, for folding, and for binding. So we know that paper has these physical mechanical properties that will change the size, its shape, is it distorted or is it flat. This all affects the register. It may affect the color with doubling of the halftone dots, and it can give you print defects like wrinkles. Cut sheet is exposed on all four edges, therefore it's more susceptible or prone to picking up moisture, where rolls or webs of paper are only exposed on the two outer edges, plus the web speeds are much, much faster, less exposure time. I recall working at the Buffalo News one year where it was a particularly very cold, dry winter, and we were getting many hundreds of complaints about the paper curling as soon as you brought it into the house from outside. Newsprint paper, groundwood, is only about 27 pounds, so it's about 2.5 mils, so it's very quickly going to pick up or lose off moisture. Generally, the heat will dry the paper, which will make it paper brittle, which will make it crack at the fold. When you store and handle paper, you should condition it. First to the temperature, always keep it wrapped and protected, and then between printings, like over a long weekend, you want to rewrap it. WIP or WIP is work in process. The conditioning to the temperature will depend on the volume of paper that you have in cubic feet and the difference in the temperature. So for example, if I have an 8.5 by 11 letter sheet size, 18.5 inches tall, about the maximum of my feeder and delivery capacity, that's 1,728 cubic inches. Those cubic inches become 1 cubic foot. So if I have 12 cubic feet and the temperature difference is 10 degrees, I got to wait 8 hours for that volume of paper to acclimate. If the temperature difference is 40 degrees, I now have to wait 36 hours or 3 days for the paper to temperature acclimate. Now, 40 degrees is not an impossible thing here. If you come off of a cold truck at 30 degrees and you bring it into a press room at 70 degrees, that's a 40-degree temperature difference, right? Again, if you expand and grow and swell, the paper becomes wavy edged, and that gives you fan-out misregister. If the paper contracts and shrinks, you get tight-edged paper. The paper looks like it's puckered in the center. It's kind of like a dish cup or concave shape to it. When the paper is dry, you have a lot of static electricity in it, which has cling. The paper wants to stick together. You get a lot of feeder trips called knockoffs, trip-offs, interruptions. It's hard and difficult to jog the paper, and you can get set off in the delivery. Again, during the summer months, we're hot and humid, and during the winter months, we're cold and dry. Too dry is static. Static causes cracking and tight edge paper. Too wet, we're wavy edge. We get a lot of fan out, a lot of misregistration, and we can get dew and condensation on metal, which will cause things to rust. So, in summary, we defined the 3 temperature scales, Fahrenheit, Celsius, Kelvin. We talked about the 3 different states of matter. We looked at the relationship between Fahrenheit and Celsius. It's linear. We looked at the sensor or the probe that made the measurements, that I could download the data into a computer, where in Microsoft Excel I could do further data analysis. Again, standard deviations, the lower the number the better. The higher the number, the more variation, therefore typically worse. We looked at the graphical plot of this tabular data. Here's the temperature. There's more variation on the high side than the low side because when it's cold, I can turn the heater on and bring the temperature up, but without any air conditioning during the hot summer months, I can't bring the temperature down if I don't have air conditioning. But the standard deviation is less than that for relative humidity. So during the cold months, low. During the hot months, high. Air conditioning brings the temperature down, which automatically does dehumidification, which is a good thing. This is a normal bell curve, but because it repeats, it's cyclical, and that cyclical pattern is called a sine wave. Here's the historical outside temperature data. You can get this for your city by going to that website. You can think of it again as a target aim with plus or minus on high, low, maximum, minimums. We talked about temperature data here, and then we talked about the consequences it has on paper. Okay, thank you for watching and listening to this video. I hope you found it interesting and informative. We'll talk to you soon. Bye now.